All right, buckle up, people. We've got screws coming up. There are a lot of funky things that happen with screws. Even though we use similar equations with your IMA and your AMA, there's a lot of extra work that goes into prepping a question for screws. So, first thing we need to do is talk about thread notation information and what's actually useful to us. We're going to talk about threads per inch versus pitch and what both of those mean. We're going to talk about how to figure out the effort distance for screws based on the tool that you're using. We're going to talk about the resistance distance for screws, and we're going to throw a calculation in at the end just because it is such a pain in the butt to work through a screw problem.
Let's talk about the last of our simple machines, which is the screw. And in reality, it's kind of two simple machines put together. We've got the wheel and axle part where you are turning a wheel that turns an axle, so we're creating that rotary motion, but at the same time we have an inclined plane that's wrapped around essentially the axle within our wheel and axle, forming that path and pitch. And what's really nice about the screw is we're changing rotary motion into linear motion. What I mean by that is we can take a wrench, we can take a screwdriver and rotate it around, and it'll make the screw go linearly instead of going radially around in a circle. They are really nice fasteners because they have a monstrous mechanical advantage, and at the same time they have a lot of friction loss, and we'll see what that looks like with our efficiency. And you've probably felt that too when you pull a screw out with the screwdriver. It feels pretty warm to the touch after you pull it out. That's because there's a lot of friction going on there, but just pulling it out by hand is not going to work out very well because of that awesome mechanical advantage. So let's talk about the details of the screws. And what's difficult about the screw compared to all the other simple machines is they have very specific definitions for DE, DR, as well as effort arm, diameter, circumference, all that good stuff. So let's go through it. For every screw or bolts, basically any threaded mechanism, you're going to be given three pieces of information. Number one is the diameter, and the diameter is talking about the diameter of the actual threaded region. It doesn't tell you the diameter of the top part of the actual threads down below. It also gives you the number of threads in every inch. So if I were to just look at an inch in my screw, I could count out 1, 2, 3, 4, 5, 6, 7, all the way up to 13 threads in that screw. So it's telling us how many threads we have per unit of area. And last but not least, we also have a thread description, whether it's coarse or fine. But we'll find out that we really don't need that information. So let's talk about the really important information that we can pull from that. And one of the biggest ideas is the pitch. And the pitch and the threads per inch, the TPI, are very much linked. So when we talk about threads per inch, it's pretty straightforward. We're talking about how many threads do we have in every inch. For pitch, what we're talking about is almost the opposite. Is if I were to rotate my screw or my bolt around once, it would give me the distance that the thread travels linearly. And at the same time, it also gives me the distance between those threads. Also, we've got our effort arm. And typically in our screw system, it's not just the screw itself. So this picture can be kind of misleading. The effort arm distance is really the tool that you're using to rotate the screw. Now, if I'm using my fingers, then this is definitely going to be my effort arm just from the center point to the outside point. If I'm using a wrench, it's going to be from the center point of my bolt all the way out to the end of my wrench. So we're not really talking about the screw itself for effort arm distance. We're talking about the tool itself. So let's dig into the pitch and the TPI a little bit before we get into any calculations. When we look at thread information, really, we don't need the diameter of our screw or our bolt. We don't even need the thread description. The big piece of information we need to get is the TPI, because that will help us find the pitch. Let's do a quick example of what that looks like. So let's say we have a question, what is the pitch? Or really we're saying the little tiny distance between those threads if there are 13 threads per 1 inch. So if we think about it, all right, I have 1 inch of space. I have 13 threads inside there. I need to figure out how much distance I have per thread. I'm going to take that 1 inch, I'm going to divide it by my 13 threads, and that gives us how much of a pitch we have. So we have 1/13 of an inch. At the same time, if I were to take my screw, maybe use my wrench or my fingers to do 1 full rotation, what's handy about that is my screw will move that same amount linearly during 1 full rotation. So my pitch is found through my TPI. It's also telling me how far down it goes per rotation into my object. So let's go through an example. Let's do IMA because it can be really specific for screws, and this is probably the most difficult part about calculating things related to screws. So we've got our IMA equation, DE over DR. We're going to modify that eventually to what screws look like. So the definition of our effort distance for a screw is 1 rotation of the effort arm. It's not the length of the effort arm. It's how far around does it go. In other words, it's a circumference. So we need to calculate the circumference of our effort arm in order to find DE. Now for DR, that is the linear distance traveled during that 1 rotation. So we can go all the way around, measure the circumference. That's my DE. My DR is how far does it go down during that 1 rotation. So we need to find the pitch, which is kind of a pain in the butt because those aren't directly given to us with the screw notation. We're going to have to go through a few steps in order to find circumference and pitch. So we can modify our IMA equation for a screw just a little tiny bit and say the circumference divided by the pitch is our IMA, or if we wanted to break it down even more, 2 pi times r, where the radius is that effort arm, divided by p, which is your pitch. So let's check out a practice example just to get the feeling of how the effort arm and the diameter and the TPI and the pitch, how all that stuff interrelates. So we've got a question. We're looking for the IMA of the screw if it's attached to an 8-inch wrench. So this is my really poor PowerPoint drawing of a wrench attached to it, 8 inches across. First things first, as usual, let's identify everything that we know, that we don't know, and the big equations that we need to use moving forward. So we know the resistance force is 1,200 pounds. We know the length of our effort arm is 8 inches from the wrench. And we know the TPI is 20. And we get that from the information of the screw. We know we have a 1/4 inch diameter. We know we have 20 TPI. And we know the coarseness of our screw itself. We don't know effort force. We don't know effort distance. We don't know resistance distance. We don't know IMA. We don't know AMA. So a lot of the things that we need in order to calculate IMA are not directly given to us. We have to go through an extra step in order to find that. Now remember, for thread information or for screw information, we don't care about the diameter. We don't care about the coarseness of our screw. The only thing we care about is the threads per inch, because that will help us figure out the pitch of our screw. So let's start out with the circumference. And we're talking about specifically the circumference of the effort arm, the distance it takes to go all the way around that screw. So we know our equation is 2 pi r, where the radius is the length of that effort arm, which we wrote over in our notes to the left. So I'm going to plug in my effort arm, which is 8 inches, and I'm going to multiply that out. And I find that the circumference of my wrench attached to the screw is 16 pi inches. Not too bad. So let's add that to our add that unknown into our known. So we've got 16 pi inches. Now we need to figure out the pitch in order to find our IMA. So let's do that as well. Now the pitch, remember, is the amount of space between each thread. And to find the pitch, we need to take the reciprocal of the TPI, kind of like what we did in the slide earlier. So 1 inch divided by our threads per inch will give us the size of the pitch, or the distance between those threads. So I'm going to plug in my TPI, 20 TPI, and if I calculate all that stuff out, I've got 0.05 inches is the space between each of my threads. And just like we did before, let's update that into our unknowns list. Okay, So we have our circumference. We grab that from our calculation with the effort arm. We have our pitch, which we calculated with the TPI. Now we can finally plug that stuff in to figure out the IMA of our wrench. And so I'm going to plug my circumference in for the numerator. I'm going to plug my pitch in for the denominator. Notice how my inches cancel out on top and on bottom. And we're left with 1005.3 as an IMA, which is huge. That is gigantic. Great, great, great mechanical advantage that we get from screw. And it kind of makes sense that we don't have to put that much effort into something gripping really, 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 really strongly. Now let's look at the flip side of that. Let's look at the AMA of our screw. So the same exact situation. We've got our wrench that's attached to our screw. We know the resistance force is 1,200 pounds. Let's say that it takes us 35 pounds of effort in order to rotate that in the problem before. So let's do our quick calculation. For AMA, it's resistance force over effort force. That's no different than any of our other simple machines. We have 1,200 pounds divided by 35 pounds, and the pounds cancel out, and it gives us an AMA of about 34.29, which is way, 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 way smaller than our IMA. So just to drive that point home, let's calculate the efficiency of our screw. So we calculated the IMA before. We just calculated our AMA. So our percent efficiency is going to be the AMA that we just found divided by the IMA from the slide earlier times 100%. And that gives us a whopping 3.4% efficiency, which is ridiculously low. That is way, 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 way low. So we got to think about for a screw, why the heck is that efficiency so low? Remember early in the video we talked about the fact that when you pull a screw out of a piece of wood or a wall with the screwdriver, it tends to be really, really, really hot. So we actually lose a lot of energy due to things like friction or to heat because of all of that surface area from the threads gripping onto the material that we're looking at. So in conclusion, think about screws as what information do you need to find in order to calculate your IMA and your AMA? So thinking about your TPI, thinking about your effort arm and the relationship between those and your circumference and your pitch to find IMA, and the fact that your efficiency is going to be extremely low because of friction and heat.